In this video, I'm going to discuss how to solve a polynomial inequality. So it says a polynomial inequality has the form f of x is less than 0, less than or equal to 0, greater than 0, or greater or equal to 0, where f of x is some polynomial. So I've written down two examples of polynomial inequalities. It's the greater than or less than symbols that make these inequalities. So these are the steps that we're going to use. We want to get 0 on one side. That's the first step, if necessary. Notice the two problems, or the two examples I put there already have 0 on one side. And then we'll solve the equal case to find what we call critical values or boundary points. And then we're going to use a number line to basically we'll put those boundary points on the number line, and we're going to use that to help us get our solution. And then we'll use what are test values to determine which intervals we're going to shade, or which intervals are solutions to the inequality. And then we'll also talk about when we use when we include the boundary points in our solutions or not. So let's just go ahead and do an example. I think that'll make it clear how this works. So first of all, we need 0 on one side. We already have that. And so next we want to look at the equal case. So let's go ahead and set this equal to 0. And to solve this, we're going to want to factor using the AC method. So we need two numbers that multiply to 3 that add to -4. And that's going to be -1 and -3. So because this is a 1x squared, we can go ahead and just write the factors x minus 1 and x minus 3. And so when we solve this equation, we get 1 and 3. So these are what we call our critical values. These are the values of x that make this polynomial equal 0. We also, you'll find in my math lab that they're calling them boundary points, which is what you will see in some books. All right, so let's go ahead and draw a number line and put our critical values or boundary points on there. Now, because we have less than 0 here, x squared minus 4x plus 3 is less than 0, we want to know when this polynomial's value is less than 0, or for what values of x is this polynomial going to be less than 0. Notice we're not including where we're equal to 0 because there's no equal sign. So for that reason, we're going to use an open circle on our grid, or on our graph, our number line. So 1 and 3 are the values that make this polynomial equal to 0, but we want to know the values that make us less than 0. There's no equal there. So 1 and 3 are not part of our solution. So we want to know when x squared minus 4x plus 3 is less than 0. Let's go ahead and put this in factored form. And so if you look at the number line here, it's divided into 3 regions. The region to the left of 1, the region between 1 and 3, and the region from 3 to infinity, or from to the right of 3. Or these are intervals. And so what we want to do is we're going to use what we call test points or test values. And we're going to choose a number in the first interval, so something less than 1. Well, 2 would be a really nice choice. I'm sorry, 0 would be a really nice choice. And then between 1 and 3, 2 would be a very good choice. We can pick any number in each region. It turns out if we test one value and it makes the inequality true, then all the others will. Or if we test a value and it doesn't make the inequality true, then none of the other values in that interval will work either. And then 4 would be a good choice as a test value that's something greater than 3. So let's go ahead and plug in 0. And again, I'm using the factored form here. I find that a little bit easier. But for some of you, you may choose to plug it into x squared minus 4x plus 3. So here we're going to get -1 times -3 is less than 0. Well, that's going to be 3 is less than 0. Well, that's false. And so 0 is not a solution to this inequality, and so no other value in that region will be. We're not going to shade this interval. Let's try 2. So we're going to get 2 minus 1 is 1, and it'd be negative 1 for 2 minus 3. When we multiply, we get negative 1 is less than 0, and that's true. So 2 worked. So any other value in this interval would work, and we're going to shade everything in that interval. Let's try 4. So we're going to get 3 times 1 is less than 0, or 3 is less than 0, and that is false. And so 4 doesn't work when we plug it into the inequality. It doesn't make it true, and so no other point in this interval will work. So you can see our final solution is going to be the region between 1 and 3, or the interval between 1 and 3. And again, we're not counting 1 and 3 in our solution because there's no equal sign for this inequality. So our solutions are the numbers between 1 and 3. So basically, if you choose any number between 1 and 3 and you plug it into this inequality, you're going to get a true statement. You'll get something that's less than 0. All right, let's move on to number 2. So notice this time we don't have 0 on one side, so we need to take care of that first. We'll add 5 to both sides, and we'll get 3x squared plus 16x plus 5 is greater or equal to 0. So let's go ahead and look at the equal case to find our critical values, or our boundary points. So we need to use the AC method here. We need to find two numbers that multiply to 15 and add to 16. So that's going to be 1 and 15. So let's go ahead and split our b term, and we'll factor by grouping here. We can factor out an x for the first two terms. So we're expecting a 3x plus 1 when we factor the second two terms. It's going to be times 5. Notice 5 times 3x is the 15x, and 5 times 1 is 5. So we're going to end up getting 3x plus 1, our common factor for these two terms, times x plus 5. And don't forget, that's equal to 0. So now that we've factored this, we can set each factor equal to 0. Here we're going to get, let's see, we need to subtract 1 on both sides and divide by 3. And so we'll get negative 1/3. If we set x plus 5 equal to 0, we get negative 5. And so these are our critical values or boundary points. Let's go ahead and put those on a number line. Now notice in this problem, we got the greater or equal to 0. So we're including where we're equal the x values that make this polynomial equal 0. And so that for that reason, we're going to include negative 5 and negative 1/3 in our solution. So we're going to put solid dots at those points. So let's see, we need to choose some test values. Negative 6 would be a good choice. Between negative 5 and negative 1/3, negative 1 would be a nice choice. Again, you could choose any number in the interval. And then something bigger than negative 1/3, let's go ahead and use 0. And so we want to know when our polynomial is greater or equal to 0. Again, you could use this 3x squared plus 16x plus 5 greater or equal to 0. You could just plug in your test values into that if you prefer. I tend to do it in factored form. So let's see, we have 3 times negative 6 plus 1 times negative 6 plus 5. So we're going to get negative 17, negative 18 plus 1, times negative 1. So we want to know if that's greater or equal to 0. That's 17, which is greater or equal to 0, so that's true. And so negative 6 worked when we plugged it in to the inequality. And by the way, it doesn't matter if I could actually use the original inequality where we had negative 5 on the right side, but I normally just used the form where we have 0 on the right. They're equivalent. They have the same solution. So we're going to shade that region. Since -6 worked, any other number in that interval would work. Let's try -1. So when you plug in -1, you're going to get, let's see, -3 plus 1, that's -2. -1 plus 5 is 4. So -2 times 4. Get -8 is greater or equal to 0. And that's not true, that's false. And so -1 doesn't work when you plug it in. So none of the other values in that interval will work. Let's go ahead and look at 0. So 3 times 0 plus 1, we're going to get 1 times 5 here, 0 plus 5. So we're going to get 5 is greater or equal to 0, which is true. And so we know that 0 works. And so any other value in that interval would work. So we're going to shade the whole interval. So now we're ready to write our solution. And again, because it says greater or equal to 0, we are including when this polynomial equals 0, which is at our critical values. That's why we had those solid dots. So from left to right, in our solution, we're going to start at -infinity. So out here, basically, to -5, and I notice the bracket because we're including -5, and then it'll be union -1/3 to infinity. So any value in these two intervals, if you plug it into the inequality, it makes it true. Let's look at number 3. So it's got 4 terms, and let's see, first of all, let's go ahead and set that equal to 0. But what I'm looking at here, it looks like this could be factored by grouping, which is the best way to factor a polynomial that has 4 terms, if you can do that, and we can here. So let's go ahead and factor out an x squared for the first 2 terms times x plus 2. So when we factor the other 2 terms, we expect to get an x plus 2 factor, and we're going to need to multiply by -4. So we get x plus 2 times x squared minus 4 equals 0. And we got a difference of squares there. We can factor that further to x minus 2 times x plus 2. So notice we have a repeated factor here. We're going to have 2 solutions, 2 and -2. So those are our critical values. Now notice with this inequality, we do have greater or equal. So we're going to use the solid dot on our critical values. Let's find some test values. Something less than -2, -3 would be a nice choice. -2 to 2, 0 would be a great choice in there. Something bigger than 2, that would be like 3. And so let's go ahead and test these values in the original polynomial. So again, I'm going to put it in factored form, but notice I wrote the x plus 2. Instead of writing 2 factors, I just wrote x plus 2 squared. So let's go ahead and plug in -3. Let's see, -3 minus 2 is -5. And then -3 plus 2, that's -1 squared. -1 times -1, you get a +1. We're going to end up getting -5 is greater or equal to 0. And that's false. So we're not going to shade that interval. Let's try 0. So we'll get -2 times 2 squared. 0 plus 2 is 2, and 2 squared is 4. So we're going to get -8 is greater or equal to 0. That's also false. So we're not going to shade in there either. Let's try 3. So we have 3 minus 2 times 3 plus 2 squared. That's going to be 1 times 3 plus 2. That's 5 squared. 1 times 25, which is 25. And that is greater or equal to 0. So we're going to shade that. And so be careful here, because the critical values are where we're equal to 0, and they're both going to be in our solution. So basically we've got -2 kind of all by itself, and then we've got this interval from 2 to infinity. So the way we're going to write that is negative 2, we're going to use braces around that. Anytime you have a finite number of numbers, a countable number of numbers, in this case there's just one number, we use braces. And then we'll union that with 2 to infinity. Notice with interval notation, we use that when we have an infinite set of numbers. So that's why we have an interval there. All right, let's move on to number 4. It's actually very similar to the last one we did. Let's go ahead and set this equal to 0. Although when we get our answer, it's going to look different. So we'll factor by grouping again. Get x squared times x plus 7. So we're expecting an x plus 7 when we factor those other two terms. And I'm going to need a negative 1 here. And so we're going to get x plus 7 times x squared minus 1 equals 0. And we've got a difference of squares there. Let's go ahead and factor that. So notice we're going to get 3 critical values, negative 7, 1, and negative 1. Now be careful when you put your numbers on the number line. They should always be in the right order. And the other thing here is notice we want to know when this polynomial is less than 0. There's no equal sign. So the values that make us equal, our critical values, are not going to be included in our solution. So we're going to use open circles on those points. Again, those are the values that make this polynomial equal 0. So test values, let's see, let's try negative 8, negative 2, 0, and 2. And again, I would always say or let you know that any other value in each interval will work. I'm just trying to choose the nicest numbers I can work with. Let's go ahead and plug in negative 8. So again, I'm going to put it in factored form. You can use the other form if you prefer. But we want to plug in negative 8. And so we get negative 1 times negative 8 minus 1 is negative 9. Negative 8 plus 1 is negative 7. So we'll get negative 1 times negative 9 times negative 7 is less than 0. So we're going to end up with negative 63 there. And that is less than 0. So that's true. And we'll shade that region or that interval. All right, let's try negative 2. It's a little tight fitting all this in here. I think we can do it though. And we're going to get 5, negative 3, and negative 1 when we simplify there. And when we multiply, we get 15, which is not less than 0. That's false. And so we won't shade in that interval. Let's plug in 0. We'll get 7 times negative 1 times 1, which is negative 7. And that is less than 0. And so that's true, and we're going to shade in that region or that interval. Let's try 2. You're going to get 9 times 1 times 3. That's 27, and that is less than 0. Or wait, no, that's not. That's false, and so we won't shade there. So finally, we want to write our solution. It'll be from negative infinity to negative 7. And again, notice we're not including negative 7 in our solution. And we're going to union that with negative 1 to 1. And that's it for this video.